At a recent CVPR talk, Phil Dewan, senior staff software engineer at Tesla, talks about foundation models and how important they're going to be to the future of full self-driving. Plus, ARK Invest shows us graphically just how far ahead Tesla is in their data lead, and that actually relates to Phil's talk. Let's take a look. Hey y'all, it's Dr. Know-It-All. So first of all, this video is related to Ashok Elluswamy's talk that I did a video on a couple of days ago. I'll list it up here and at the end of this video. And there are several other talks that I've related this to as well. I'll put those links in the description. So basically, this is video 4 out of 4 on related topics about foundation models, the complexity of reality, and how building out new models is going to help Tesla. And as opposed to Ashok Elluswamy and others at Tesla who are, relatively household names, you may not know about Phil. So he is the autopilot occupancy network, object detection, behavior prediction, auto labeling, and online perception lead at Tesla, or at least those are the areas he works in. Obviously, that is a lot of hats that he wears. And so kudos to him, and obviously for the rest of the folks on the team that are working on these projects. A lot of this stuff is done in the background without any real recognition. And so I think it's important for us to, once in a while, just give people a little bit of a round of applause for the amount of work that they have to do in the trenches to make all of this stuff work. Also, as Phil's talk is highly related to what Ashok's talk is about, I'll forgo discussing some of the stuff that I discussed in more detail in his talk. Just briefly mention it. Mostly I'm going to focus on the differences. So my recommendation, not that you have to pay attention to that, is to watch that video either before or after this one, it doesn't matter. And then of course, go watch the original talks, both of them. I'll leave links to this stuff in the description so you can check it out yourself. But I think hopefully after watching my talk, you will be able to understand the original talks in more detail. And of course, I'm just touching on individual things that I find interesting. And so you might get more out of listening to those talks, but hopefully listening to what I have to say about them first will help you. Don't know. Also, thank you so much to folks who have sent me good wishes about the whole COVID thing. I am definitely feeling a lot better than I was yesterday. So hopefully the increase will continue. This hasn't been a particularly bad bout of it. I had my first bout about 11 months ago, and that was pretty awful. This one has been, I actually just thought it was a cold. I tested because I just wanted to be sure. And then I was like, oh gosh, I actually am testing positive for COVID. So I wouldn't even have known normally, except I was a little bit extra tired. And that was what kind of made me suspicious about that. Anyway, that being said, let's talk about Phil's talk. So you'll see this first graphic is more or less the same as what Ashok had, so I'm not going to go into a lot of detail about that. I think the one thing that's worth calling out here is the 36 frames per second. I believe that when Phil discusses this, he means that the cameras are operating at 36 frames per second, which is what they're taking in. But I think what he might be meaning instead of that is that they're actually operating at 36 frames per second for the entire stack, which means that it's running 36 times every second. It's making decisions 36 times a second, which is a really good rate, right? Now, I know people are like, oh, 60 hertz is what you want for like your gaming devices and things or above, but 36 times a second to make a decision about whether to press an accelerator or a brake or turn the steering wheel a little bit, that seems like a reasonable amount. That's a very, very fast decision-making process, and of course can allow the car to drive very, very smoothly relative to the way that we sense the world. And if you want a comparison, we see it somewhere between 12 and 15 frames per second, something like that. If you show a video that's like 12 frames per second, we can usually just barely tell that it's individual images. But of course, even 24 frames a second, which is what theatrical movies are shown at, we can't tell that those are individual frames. So human beings are operating at about 1/3 of 36 frames per second, and we still manage to do just fine. So, so I feel like 36 frames a second, if they are truly running at that rate, seems like a very, very good, solid, frame rate to be running at for making decisions about the vehicle's motion. And if that is in fact the case, that is just really amazing that they were able to cram so much stuff into 1/36 of a second. And then I want to inject a slide from ARK Invest into this discussion because it's going to be important later. But this graphically really shows Tesla's advantage in data collection. So this is a graphic that they have called time taken to reach the most recent 1 million miles. So Tesla, if you look back at the slide previously, they've got somewhere around 250 million miles and growing of data that they've collected from full self-driving. You can see that according to ARK Invest, they believe they're doing that in approximately 14 hours. hours, or around about half of a day. And you can see that Cruise is about 3 months to collect 1 million miles of data, and Waymo, shockingly, is about 2.5 years to collect that much data. And so if you go from Tesla to Cruise, you're looking at about 150 times. So Tesla is collecting data about 150 times faster than Cruise and like 1,400 times faster than Waymo. So those are staggering numbers. And the other thing is that Tesla, the more Teslas Tesla sells, which is every single day, more Teslas are coming out on the road. I believe this is only counting North American drivers, but still, it doesn't matter. Every single day, there are more Teslas coming out on the road, which means that Tesla's collecting that million miles of driving faster and faster and faster, whereas Cruise and Waymo are not able to scale nearly that quickly. So they can't easily reduce the amount of time it takes to collect 1 million miles of autonomous driving. So not only is Tesla way, way ahead, 150 times or 1,400 times ahead or faster right now, but the lead is only going to increase over time. So it was worth pulling this out, and we're going to talk about this more later in relation to Phil's talk. So I thought it was particularly good to put this in right here. So next up, and to show the generality of Tesla's autopilot software, their full self-driving stack, Phil explicitly calls out the fact that they're able to run Optimus, the humanoid robot, on the same stack, basically. And Optimus has 200 plus degrees of freedom body control, which means, wrist motion, finger motion, not head motion, torso motion, lifting the legs, all of that kind of stuff. There's 200 degrees of freedom that this robot has, as opposed to about 3 degrees of freedom, or maybe 4 if you want to count the steering wheel moving both directions as 2 degrees of freedom. But anyway, it's many, many, many times the degrees of freedom of a vehicle, and yet you're able to run the same software stack, the same perception stack, the same basic understanding of the world stack on this humanoid robot as a Tesla vehicle. And that is really pretty cool. And you're able to run it on the same hardware as well as the same software. Phil says that it runs on the same stuff that's in all the cars that are out there, but that would be hardware 3. And I strongly suspect that they are running on a modified hardware 4 chip. In other words, it's a hardware 4 motherboard, but it's cut in half. From what we've seen, it's only running half of hardware 4. Doesn't make sense to me that they would run this on the older hardware 3 hardware, but anyway, regardless, it's either on the old version, which is what he explicitly says because he shows a picture of the hardware 3 board, or more likely it's on the new hardware 4 board, but that is already on vehicles that are out there. So anyway, whatever that is, it's basically running on the same software and the same hardware as the vehicles. And that's pretty darn cool that the solution that they've come up with for driving is generalized enough that it works for a humanoid, 2-legged, 2-armed robot, as well as a vehicle with 4 wheels robot. So as Phil discusses in his talk, as they built this stuff out, they started to ask themselves questions about what is foundational, not just for the car, but basically how do you extend this to work in any sort of circumstances with any given type of robot? So that is kind of the North Star that's guiding them now. That's the thing that they're thinking about. So no longer are they thinking about only full self-driving a car, but they're thinking about autonomous robots in general. And how do they guide their hardware and their software stack to make sure that they work in that generalized situation? And that's where these foundational models come in. And in the video about Ashok's talk, I didn't really call out foundational models and what they mean in a great deal of detail because I wanted to wait for this one. But anyway, foundational models, the easiest way to think about this is to use large language models as an example. So ChatGPT is not a foundational model. What is GPT, Generative Pre-trained Transformer. So ChatGPT is a bunch of stuff that's put on top of something that was a foundation model that was built separately. So what do you mean when you build a large language model, foundation model? What you do is you read in trillions of words from the internet and from other data sources. In other words, it's language, so you just read in language, trillions and trillions of words of that language. And you use autoregression, which means basically that you give it some number of words and then you block out the rest of the sentence and you say, predict the next words in the sentence. Well, you already know what the answer to that question is because you've got the rest of that sentence there or the next sentence after that or something. So you can have the computer train itself. You don't have to have people telling it whether it's right or wrong because you just use the rest of those sentences to tell it whether it's right or wrong. So that foundation model gives you the basis upon which you can then use reinforcement learning through human feedback and other things on top of that to create something that will make human beings happy, which is the Chat GPT. But the GPT that's underneath it, that thing, if you use that directly, it gives you really weird answers. It's not aligned with what humans want, but that is the foundational model upon which you can use a relatively small amount of compute to build the fine-tuned different projects that you're interested in. And that is exactly what Tesla is doing here. They're building out a world right now where they can auto-regressively train their vehicles, and of course Optimus when that comes in. And I'm not really going to talk about Optimus much more in this video, but just assume whenever I talk about the car, I'm talking about Optimus as well. But what you can do is you can build out a world where the car can be questioned all the time. What would I do next? What's the next thing that's going to happen in the next couple of milliseconds, the next couple of seconds, whatever. Just think about it like a sentence, right? You're blocking out the second half of the sentence. Here, what you're doing is you're driving the car a certain distance in time or in space, and then you're saying, what happens next? What happens next? What do you do? What happens next? What happens next? And that is the really, really important foundational model that they are building. And then what Phil talks about in his talk is the parts building the heads. He calls them heads. They're little extra things that stick out of this foundation model. Building that is relatively lightweight computationally once you've built this foundation model that's underneath it. And of course, that relates to what I was talking about in Ashok's talk about world models and how you have to build something that can create its own understanding. It generates its own understanding of the universe. So keep that in mind as we talk about the rest of this video and everything. So the next thing that Phil talks about is shared occupancy networks, where he shows Optimus on the right and the vehicle on the left. He specifically says that it can use the same network with minor tweaks for both a car and Optimus. And when you look at this, you can see that the voxel size, the cubes, the little cubes of the world in the car on the left are relatively huge compared to Optimus. I'll move myself out of the way a little bit here, but you can see that these cubes are relatively small. They're a few centimeters on the side, where these are probably some tens of centimeters on the side. So even though you've got a very different output, you're able to utilize the same network. And the trick that they use is they have a latent space that they compress all of this stuff down to. And it's only a question of when you reconstruct the 3D space out of that latent space, how many deconvolutions do you do essentially? How much do you upscale this whole thing? And that's where you can actually affect the resolution of what's going on. And it's a really, really cool dynamic system. And Phil kind of downplays this, but it's a bigger deal than you think, because totally different environments with different semantics and all of that stuff are able to be utilized by the same network. In other words, a vehicle running down a road has very different semantics, different things that it's dealing with than a robot in an office space, and yet they're still able to utilize the same network. So it's a really big deal that they're able to make this work in such a generalized manner. And one other thing that's really interesting is when he talks about the flow network, which is the moving this occupancy network through time and dealing with vehicles and other things that are moving, he says that they don't make any assumptions about the shape or the motion of these objects. In other words, it's not predicting kinematics. It's not figuring out exactly what it is, whether it's a human and stuff. So it's this layer of occupancy network is relatively dumb. It doesn't make assumptions about things. There are later heads that are put on this that associate specific blocks with specific things and give more information and allow it to say, oh, that's probably a person or a cyclist or something like that. What is the likely kinematics of that person? Might they be able to pull into my lane? How quickly can they travel? All of that kind of stuff is sort of layered on top of this occupancy network. And critically importantly, this entire thing runs in 10 milliseconds, or about 1/100th of a second, which means that if you're running at 36 frames per second, you have a lot of extra room to do other calculations, because this only takes 1/100th of a second to do. Next up, Phil is going to talk a lot about architecture, and we're going to sort of utilize this graphic here with some extra things pasted on to the end of it as we talk through this. Unfortunately, there's a piece of his talk that is cut off, so there's a little bit missing at the beginning of what I want to show you, but I believe what it has to do is with not processing photons. In other words, the input to the cameras is just read in directly from the world of photons. It's not processed into images like a human being would see. Rather, the pixels are just taken in directly and used as data sources.
It also helps with latency. Able to remove ISP in the loop, and it is we don't even do any tone mapping at all, and all the images generated here are actually done post process just for human eyes. We take these images and we rectify that with the camera calibration. And we then feed these rectified images into a set of RegNets and BFPNs to extract multi-level image space features. Then we construct a set of 3D position queries along with the image space features as keys and values, and we feed them into an attention module.
So I just want to break in here. This thing where they talk about spatial, well, where he talks about spatial attention right here, this is transformers. That's a transformer. The key query value thing that he's talking about here, that is transformers. And if you hear people talking about transformers, that's where it's located in Tesla's software stack. So you get the image features that come from the cameras. Those are messed around with by FPMs and RegNets and stuff. And then they're fed into this attention layer. And transformers are all about attention. They're like, they look back and forward through space and time. And they're like, what's interesting to me? What do I need to care about? Given what I'm seeing here, what do I need to care about over here or back here in time or something? So that's what's happening here. And I just want to point this out because a lot of people, I think, just hear the word transformer and they're like, no idea what that actually means, whatever. That's all it is right here without getting into the architecture of how a transformer works. That's where it actually is. And it's all about attention.
The output of the attention module is some high dimensional spatial features. And we align the spatial features with vehicle odometry to create, to capture motion. And this is kind of like a simplified here, but it's a lot of work done happening here to just make sure the vehicle odometry is done correctly to recreate what happened in the car and to align the features precisely. So, and after we do this, we're able to create a very rich spatial and temporal features, which we then pass through a set of deconvolutions.
And again, just to stop here really quickly. So what we get out of this whole thing is what's called a latent space. It's a compressed space. You could think of it as a spreadsheet with a bunch of numbers, and all of those numbers mean something magical. It's the mystery of neural networks, is that latent space is very, very high dimensional, very, very highly compressed information that's in there. But in order to make that useful in situations like this, what you have to do is deconvolve it, which is basically you take it and you shrink it down when you're convolving it down to something. And if you've ever heard of convolutional neural networks, that's what they do. They convolve things. So they run a filter over something and they shrink it down and shrink it down and shrink it down. And deconvolution is the opposite. So when you've got this very, very compressed vector space of latent space there, you're deconvolving it to pop it back out to your three-dimensional world, which is what you're interested in the end, because you need to know what's around you in the three-dimensional space, not simply have this high-dimensional latent space that you're working on. And this, of course, that deconvolution step is what I was talking about, when you can vary that deconvolution step to deconvolve it to small voxels in the output for something like Optimus, or if you're driving very slowly and parking and you want a lot of resolution, or bigger voxels if you're driving quickly and you don't need to have that much resolution, or if something is far away. So it's in this deconvolution step right here that you can actually make changes to the network, and you can see that's after most of the work has already been done, so it's relatively lightweight to do that, which is the reason why Optimus can be run on the full self-driving stack without too many adjustments.
To provide the final output for the volume, which included occupancy flow, semantics, and so on and so forth. But the output of this volume is in a fixed-sized voxel grid, which is not precise enough for control. As you know that, when things are close by, you have to really know these dimensions very precisely, and things are farther away, probably does not matter that much. And the way we solve this problem is that we also predict feature maps on a per voxel basis, and then we feed it into those per voxel feature maps into a set of MLPs with a set of 3D positional queries. So as the output of the network, we can query any 3D positions around the car to get the output.
So as I was saying, that's the step that he's talking about at the end, creating those queryable outputs where you can affect the size of the voxels and what you're interested in a dynamic sort of fashion. You don't have to pre-decide anything way back at the beginning. You can actually decide it at the end of this entire process, which is really, really important to the flexibility of this network. So next up, what Phil does is he adds this thing called surface outputs here that I've got outlined. And what that is looking at roads and adding things like roads and stuff like that to the original information, which was fixed location type things like cars and trees and buildings, stuff like that. If you already watched my video on Ashok's talk, then you'll know that he discussed how pernicious and obnoxious roads are because they have very, very long extent. They're basically infinite. They just go and go and go. They don't have finite representation in space, which makes it much more difficult. So creating this surface output thing and adding this to it and attaching both of these together was a really, really big step on Tesla's part. And that was one of the things we saw first at AI Day #2 last September.
Besides this voxel gray, we also predict surface output. And the surface has both 3D geometry as well as semantics. So by semantics, I mean we also capture the color of the surface and all the road markings on surface, whether it's a stop line, lane lines, or like any yield signs, stop signs that are on the ground. And we found this to be incredibly helpful for driving in unusual driving environment such as San Francisco, which has a lot of hilly road and curvy road, where knowing what the surface looks like in 3D space removes the flat world assumption, and we found that incredibly improve our driving smoothness. So, and the surface or the volume are actually not output separately. In fact, the volume output is actually aligned with the surface implicitly, so that when you go through a different surface area, the voxels does not move up and down. It always just aligns with the drivable surface. And as we can see from this video here, the car is going through a hill crest area. You can see this 3D shape of the surface very nicely, and it aligns with the voxel gray as well.
So again, Phil makes this sound relatively straightforward, but this must have been a nightmare to get this to work. But basically, you've got kind of an infinite surface, a very complex reality that you're projecting into a relatively abstracted surface. That's the blue thing that the car is driving on. And then you have to implicitly attach the voxels of everything to that surface. So what you don't want to do is have the car driving over the top of this hill in San Francisco and suddenly have all the buildings and the ground and everything jump up in the air and then come back down again or something like that, which is what would happen if you didn't align these voxels with the road surface. So how they did this is a little bit of a mystery. They don't really say, but somehow they attach these things together. And that is really, really critical because it keeps everything stable and solid. Otherwise, if things start jiggling around too much, then the car is going to lose confidence about where it is. So even over hills and things where he says you remove the flat world assumption, which you can do with a lot of roads, but there's also a lot of roads you can't, where you go over, humps and things. And you have to be able to remove that flat world assumption and keep things attached as you move across a three-dimensional space that, has hills and valleys and things like that. Next up, Phil talks about this 360-degree distance field, which is the kind of thing that you need to do when you're parking. Traditionally, with cars that have some sort of auto park capability or those things that warn you if you're getting too close to things, they use ultrasonic sensors, and older Teslas, of course, have that, like our Model Y, but the new ones don't. Our Model 3 does not have ultrasonic sensors, and yet it's still able to park, and the reason why it can is because they've created another module on the end of this thing that allows it to see around itself in 360 degrees. You get that pretty top-down view where you can see the car, all the cars around it, how far it is to like other things like curbs and things like that. It's very, very cool how all of that works.
We kind of built this network and it runs in the car for about, I think, probably almost 2 years now. And then it works very well. So we start to think, what else can we build on top of this? So early this year, we had this very fun project where we start to predict a distance field around the car on top of the Occupancy network. So this is literally just put a small head on top of the network and do a regression test to get a distance field. And we then show this distance field on UI for customers as a manual driving feature.
So again, I just want to point out when he said that they're just putting a head on this model, just look at what's going on here. You've got this big model with a lot of computation, and what they're doing is they're building out little heads on top of that. And these are relatively lightweight. You can use a regression system to figure out approximately where it is from everything else around it. But the deal is, once you've built this sort of foundational model, adding these extra heads on top is not that big a deal, and it doesn't take that much extra compute power. So it's really, really cool how they've built out this basic model that you can just add other feature heads onto to get it to do different things that you want it to do.
For parking or maneuver through very narrow area. And this is the video with one of our customers doing a parallel parking. And you can see from the right side that this contour is generated by this distance field. So compared to like traditionally, usually this is done with ultrasonics, right? So we just most of cars have ultrasonics on the front, on the back, and trying to just measure the distance directly. And the advantage here is that first we have 360-degree coverage. Let me just play this video one more time. And then it also is able to capture the obstacles at different height because we don't have this sensor limitation. For example, the curb, and ultrasonics is usually pretty bad with S-curve detection. And third is that it covers arbitrary range, right? So we don't have like a range limit from the ultrasonic sensor anymore, and it's able to basically capture according to as large as what we want from the occupancy network, and we just show as a range that is comfortable for the driver to use.
And then Phil continues on to talk about how as they built these tasks at the end of the model, they realized that what they were doing was building a foundation model. And one of these, the tasks, of course, are outlined in the red, where the foundation model is in the blue, or at least the central part of the foundation model is in the blue. So they realized that the main task is the world building in the middle section, in the blue section, and that these tasks can just be, tacked on at the end, given whatever task they want. So the goal became to create as generalized a foundation model as possible.
So this vision-based park assist is just a small application. But while working on this, we realized that this model actually has really rich features that's able to capture a lot of things going around us. And so we started to think, okay, how can we navigate this and build a really strong world model? So if you zoom out a little bit and look at this network, right? So the bulk of the network, all it does is really just create this world model in the vector space features. And this kind of ties to the previous talk where, we really want to just build like a really nice 4D world model to understand the world. And once we do that, all the downstream tasks are actually just tiny heads that is very easy. And we can just like plug in, do some fine tune on that. It usually just works very well. I couldn't find a very nice picture to capture this, so I just put a Tesla logo there to represent the vector space features. So, but what we're really looking for from this direction is really just like how do we build this 4D space world model feature, and then we can just use that to capture everything we want for driving, for humanoid robot, or for anything that related to embodied AI.
So this is really the crux of the talk. He's talking about building a 4D representation. I've called it previously gamifying things, whatever. It's like turning the real world into a video game. And the advantage that you have about that is it's all vector space. It's a three-dimensional space that a computer understands, because of course a computer is great. If you tell it that something's at an X, Y, Z and time component, it can track that thing. It knows where it is. But the question is, how do you get from reality, which is super fuzzy and doesn't have that, into something where a computer can actually understand it implicitly, because that's the representation it uses. And that vector space that he's talking about right there is that thing. And so all of the work that goes into this to create that vector space means that once you've accomplished this task, once you've built that foundation model, everything else is just an output from that, and it makes it so much easier to do all of the other tasks. And rather than build all of these models that do individual things, they're just like, we're just going to build one big giant thing that does it all.
And if we do this correctly, we'll be able to use this feature to capture everything that is relevant for driving, whether it is the aforementioned, a volume or surface, which has all the information we need for understanding where to go, and for objects, for lanes, and for traffic control. And we, instead of trying to build different models to tackle each one separately, we really want to just like build one model that does everything together. And traditionally, we shared a lot of features from image space, which just extract the 2D information. That information is actually not quite enough for doing this kind of foundation model. And now, since then, we have changed our approach to actually combine everything in vector space, so that we just need to build one model that does everything very well, and then then connect them with different tasks.
So this model, of course, is incredibly powerful, highly generalizable. It does everything everywhere all at once, basically. It's the everything bagel. Maybe that's what this entire thing should be called. They should rename their network the everything bagel. But it, instead of having to build all of these little models and all of these things, they can take them all, they can do them all together. And that is incredible, because then you can just, all of the needs that you have, you just plug something in. So if you compare this to what Tesla does in hardware, they have things called known stable interfaces. And that would be where you have the front of the car and the middle of the car go together. And there are these plugs that fit those things together, and those remain the same. And you can mess around with all the stuff inside of each one of these things as long as the known stable interface remains the same. And what we're talking about here is this foundation model. It produces a known stable interface. It produces an output in a vector space, in a compressed latent vector space. That would be this area over here. Oh, sorry, this area over here in the spatiotemporal features and everything. As you get to the deconvolution, you can then project it out into different areas of what you're interested in. So that is just incredible. But the problem with that, of course, as you might have suspected, and the reason why, again, people don't do this very often, is data and data management and fleet learning and all of that kind of stuff. And that, again, is where Tesla has, an advantage that just nobody else has. And as I discussed this at more length in Ashok's talk, I'm not going to go into huge detail here, but basically you can utilize the fleet's compute power, all of those computers that are sitting in Teslas, to do data mining, which is this area over here. Pull out the interesting stuff that you want, the weird stuff that's not working right. You can then pull this into a ground truth. You can update your model, and you can repeat the cycle and repeat the cycle. So you've got a flywheel that's going on in order to make this happen. And of course, transformers and foundation models, they both need just massive amounts of data to train on in order to work. And that's where Tesla has this huge advantage at being able to not only get data, but get clean data and get exactly the data they need by using their fleet to grab that data. And one interesting little tidbit is that Phil says that most of the team spends most of their time working on data and data collection, not the original model that's the foundation for this thing, which makes a lot of sense. I mean, a lot of what goes on with modern machine learning is all about getting data and cleaning data and figuring out what data you need and all of that kind of stuff. So the neural network model itself is probably not tweaked very often anymore. It's probably like, oh, this works pretty well, and we'll make changes to it as we need to. But most of the work is actually done on this slide right here, which is getting all of the information and getting it into some sort of ground truth model, and then you can update the model. But all of that mining, collection, labeling, ground truthing, all of that kind of stuff is what they spend most of their time working on. And then, of course, we have this really interesting slide, which again tails into what Ashok talked about, so I'm going to go over this relatively quickly. But they can use multi-trips and nerfs to create a 3D reconstruction of any scene. So basically, any intersection that they go through, any road that they drive down, as long as multiple Teslas or the same Tesla at different times of day and multiple times has driven through this area, they get many, many instances of that. And they can combine those together to create a very, very high resolution truth, ground truth map of what's going on in that area. Not just roads, but also, sidewalks, curbs, buildings, trees, stop signs, whatever else you need to have, they can grab that by getting this multi-trip reconstruction done. And just to reiterate how important this one model to rule them all is, Phil talks about that again here.
And this year, we extend this same approach. Besides names, we start to model everything. So this is a 3D reconstruction from multiple trips of Teslas in the same area, and we put together. All this is generated from 8 cameras of video streams, and we put together through different trips. And you can see that it's able to capture all this very high quality information, and we can use that to train all kinds of stuff to make sure the world is consistent. And all this data is very rich in terms of that. We don't have a separate data set just to provide one ground truth anymore. We just have a unified data set that captures everything we need to train such a foundation model.
And on that note, Phil wraps up his talk. I think it's, again, important to reiterate that what he's talking about here is not building a whole bunch of different models to do different things, but to build one giant foundation model that the computer can basically train itself on. The neural network can do auto regression, and it can figure out the representation of the world. And again, that ties into Ashok's talk as well. And it's very, very intriguing, the possibilities that they have. And then we get to a really interesting question and answer session, and I highly recommend, it's about 15 minutes long. I highly recommend listening to the whole thing at the end of the video, obviously. But I want to call out 2 questions and answers specifically. The first one is a question about end-to-end neural networks with version 12 of the full self-driving software, and listen to what Phil has to say about that.
Yeah, so that's a good question. Yeah, so basically we're building this network. So it's not really the occupancy network anymore, right? So we're basically building this foundation model to capture this world model, and we think that will be essential to use for end-to-end driving. And as for the end-to-end driving application itself, we're not ready to show what we have done so far yet. And I guess stay tuned.
So yeah, wink, wink, nudge, nudge, stay tuned. But you heard Phil specifically say they're not even using the occupancy network anymore. That thing, again, is a stepping stone to what they're building. They're building a foundation model that is basically, again, he's saying stay tuned, but it sounds like what they're talking about here is they're building out a model that is able to build a representation of the world from the ground up on its own without needing labels and without needing human intervention. It can do it auto-regressively inside of this world by building and refining this vector latent space that is highly, highly representational of everything that can happen in the world. That's a pretty intense and amazing project that they're working on, but it sounds like, again, wink, wink, nudge, nudge, that there are things that are going to be coming up and more announcements will be coming soon about this. And next up, Phil gets a question about the advantages of occupancy networks and what comes up after that. So kind of the same sorts of things here. So again, listen to how he answers this question.
So so there are basically quite a lot of different representations for like this occupancy, right? So we use kind of dense voxel gray, and you can also do any other representation, implicitly, SDF, this kind of stuff. So the as I described in the slide, basically we have this dynamic resolution thing, which is a way to help us to make the network actually small enough to run in real time, right? So we don't just like naively say, okay, we need X centimeter resolution, so we have to segment the entire world in such thing, which is obviously not scalable. So I would say that the dynamic resolution thing we did here is one of the main reasons that we're able to actually achieve a high perception performance while running incredibly fast and efficient. And a lot of advantage we have is also with our own neural net accelerator. Basically, we build in-house so that we're able to actually accelerate this with what we need. And I kind of just said that in like one sentence, but it's an incredible amount of work actually happening in the background just to make this thing run fast enough in the car.
Okay, thank you. So what's the next? Is there any idea?
Yeah, so the next idea is that I would say that basically the occupancy thing is really just like building these features for the world model. We eventually, it's not gonna I don't think we'll explicitly be driving on top of that. So these features give us this 4D understanding of the world. And I think the next steps, a lot of next steps will be really just like on the application level. How do we derive different applications in a very lightweighted way to represent different scenarios?
So there's actually a lot to unpack there, but the first thing is, again, he reiterates the dynamic nature of the occupancy network and how it's not fixed voxel size, but it can change. But more importantly, what he said was, he says they're not going to be driving on the occupancy network. In other words, they're not going to be using that. They're using it to build a foundation model. Now, he's making it sound like this is future stuff. I almost guarantee that they are working on this actively right now, probably have some alpha builds, at least in a virtual world, doing this. But then at the same time, the occupancy network sort of taught them how to understand the world, how to create a 4D understanding in a latent space of the world itself, and then turn that into a usable vector space in the projection of that. And the consequence of that, as he says, is that they're going to be able to create these lightweight heads that just plug into this foundational model. So if you want, again, to compare this to large language models, that would be that reinforcement learning through human feedback. It's like, what do humans want out of this? Well, humans want like a parking situation where we can see these kind of things. Humans want the car to be able to navigate from one place to another. These are all sort of little output things that it can then utilize to create something that makes us happy or makes the car do its job. But those things are relatively lightweight computationally and everything once you've built this foundation model. So the foundation model is the kind of new occupancy network. It's like occupancy network was a stepping stone to get to this foundational model. And once we get there, we're not going to need that anymore. So a lot of that old stuff is going to be scrapped. Or perhaps better put, it's going to be subsumed into a model that's even broader than what we had before. So I know this is a lot to take in, but the big takeaway is stay tuned to what Tesla is going to be doing in the next 6 months or so. I, for one, I really hope that they do an AI Day 3 sometime in the fall, like September, October, because at that point, hopefully they will be willing to announce what they're working on with this foundation model, this world model that they're building, and talk about it in more detail, because this is really exciting. And again, if they can get this all working as they think they'll be able to, both Phil and Ashok have said, this model could become something that not just drives your car everywhere, but also operates the robots that you're around and does a whole bunch of things that we haven't even thought of yet. This is the kind of foundation model that really could change the world, not just the world of driving, but the entire world in which we live. So as Phil says, stay tuned. All right, I hope you enjoyed this episode and found it fun and interesting and thought-provoking and quite geeky. If you did, please do like it so other people can find it. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon, my YouTube channel members, and my Twitter subscribers. Thank you all so much for your support. I truly do appreciate it. And of course, if you want to join any of them, just check out the links in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a car, a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.